Yo, it's your boy Dr. Clement.
So proud of you, Kara. So proud. All right. Anyway, yeah. Yeah, it was worth a shot. Okay. All right, so guys, here we go, though. Talking about natural logarithmic functions. Again, you've seen this before. You've talked about logs, or if you've talked about logs, you've talked about natural logs. So in an Algebra 2 setting or Algebra 3, if you were there last year, you definitely would have gotten some work in with the natural logs. Now, how much graphing you got in with natural logs, I don't really know. I would assume not much. The really good news, though, is that if we make a solid connection that natural logs are just simply log base e, then really what's the difference if you have log base 5 or log base 7 or log base e? My hope is that we get to the point where we recognize that the difference is actually very slight. Sure, we're going to be dealing with some decimals along the way, but our pattern doesn't break. Our approach to the problem is going to remain the same. So just as a couple reminders here, e, it is a number. It's not a variable. It's that number, again, being approximated here, approximately 2.718281. But again, e is going to be the base in the natural log that we refer to as ln. So anytime we see ln, understand that what that really means is log base e. You will never see it written this way, but again, just so we can start to wrap our mind around it, log base 2.718, that natural log. Okay, so highlighted in yellow is what we really want you to take away from this. You're used to writing it this way and seeing it this way. What it means, once again, is log base e of x. And as long as we make that connection, that natural log is just log base e, just like we have log base 10, like we have log base 2, like we have log base whatever. It's just a log with a specific base. It just has a lot of applications, okay? So a couple things to discuss here. Let me make that a little bit larger so we can see it a little bit better. All right, so as we're taking a look at this, we're saying y equals the natural log of x and x equals e to the y. We're saying that those are equivalent statements. So if you recall yesterday, we would have talked about something like this. If we had x is equal to log base 5 of 125. The equivalent statement here would have been base is 5 raised to the x equals 125. We would have said that these were equivalent statements. Say that, Joseph. And we can see the connection, right? We can see very clearly where that base came from, where everything. We don't see it as clearly here until we take the extra step of saying, all right, well, yes, it says y equals the natural log of x, but could we assume that what that really means is log base e of x? And as soon as we write it out this way, now hopefully it's making more sense. E to the y equals x. Then we can start to see how and why those are equivalent statements. So please don't forget all of those properties that we have in place for logarithms. We're going to have very similar versions in place for the natural logarithms. Okay, so more than anything else, we call them properties. Technically, I like to call them shortcuts. Honestly, that's the way it's going to feel more often than not. Anytime we see a natural log of 1, that's 0. It's just a fancy way of writing 0. The reason for that, again, let's not get it mixed up or complicated. If yesterday you had log base 5 of 1, we would say that that would equal 0 also, wouldn't we? Because 5 to what power equals 1? Well, 5 to the 0 power equals 1. So the point that we're trying to make is that if we have an e, I'm really scribbling and making a mess here. If we had e, it's the same story. E to what power equals 1? E's a number, so e to the 0, that's how we're going to equal 1. Okay? So the shortcut being, once again, that if we ever see natural log of 1, we know immediately that's going to be 0. Okay, same story if we have the natural log of e, that's going to equal 1. Anytime, every time we see that, again, this is that same version of if we had log base 5 of 5, something like this, we would say, well, 5 to what power equals 5? Well, obviously 5 to the first power equals 5. Again, it seems very clear when it's written that way. It seems a little less clear, but anytime we see the natural log of e, that's just 1. Fancy way of writing the number 1. Okay? Those two properties, natural log of 1 is 0 and the natural log of e is 1. Those two things are going to show up quite a bit and save us a lot of time over the next few sections. All right, the one-to-one property is still absolutely in effect. Again, we talked about yesterday how log base a of x is equal to log base a of y, only if these of values x and y are the same. Same story here. The natural log of x is equal to the natural log of y, only if x is equal to y. This hopefully it makes perfect sense. What we can do now is if you have something like the natural log of x is equal to the natural log of 3, now we know that x is equal to 3. I hope that it seems and looks stupid if we had something like the natural log of 17 equals the natural log of 3. Hopefully we've realized very quickly that no, it doesn't. Right? You can type that into a calculator and you're going to get decimal values. There's no way that the natural log of 17 is the same as the natural log of 3. The only way that they are going to work is if those of values match. That's what the one-to-one properties say. It's no different for natural logs as it was for any other log base. Okay, I think we can skip that example. The inverse is going to be true as well. We talked about this one yesterday. If you have log base A of exponential base A, these are going to cancel out. Okay, same story. If you have exponential base A raised to log base A, that's going to cancel out. So the same thing is going to happen here. If you have the natural log of e to the x, these are going to cancel, and we're just left with that x. Or if you have e raised to the natural log of x, together these are going to cancel, and we're just left with whatever that x value is. So how that might look is if we're doing a problem like this, I'm assuming that none of us are interested in trying to find 6 to the 20th power. Your calculator's not interested in it either. It's probably going to give you some error message. But what we can do now is we can recognize, well, if we had this, 6 to what power is equal to 6 to the 20th, this is just a one-to-one problem. X is equal to 20. That's what we're saying. But if we didn't want to go through these steps, could we have looked at this and said, well, log base 6 of 6, they cancel, we're just left with 1. So do we see how there's a shortcut that is an option? Now, are we going to see every shortcut every time? Probably not. We're going to miss a few, but when we see them, again, they're exactly that. They're intended to save you a little bit of time along the way. It's not going to be this is going to make the difference between a problem that takes 1 minute or takes 45 minutes. It's not that big of a shortcut, but if it saves you 20 seconds here or there, then obviously it's probably worth taking. All right, so guys, what I wanted to work through, if you were to take out your, again, we could graph this one that's on the note sheet, but I would say let's go ahead and tackle number 7 directly from your yellow worksheet. So number 7, we see y is equal to the natural log of x plus 1 plus 2. Okay, so I know that we're kind of pinched on time, but what I would encourage you, anytime you're graphing natural logs, realize what natural log really represents. That's log base e of x plus 1 plus 2. I'm not saying that you need to write this out, but what I want you to be thinking about is just y equals log base e of x. Again, what I'm really trying to stress to you today, I'm sure you've already picked up on it, is that when you're in this format, it doesn't matter what your base is. What do you know you're going to start with? 1. Point at 1, 0, vertical asymptote on the y-axis. So we know that that's going to happen. Now where it gets a little bit weird, in this particular case, is how we find that second point. It's still over the base up 1. It's just that our base is e. So we're going to go over e up 1. Now we know that e is approximately 2.718. So again, trust me, I'm all about precision. I want things to be as exact as possible. But I cannot assure you or anybody else that that point is exactly at 2.718, 1. If we labeled it as e, 1, yeah, that's exact, but I don't know if my graph is exact. All right, so this is the parent function. This is the sketch. Thinking transformationally now, hopefully you can see this. Where are we going? Left 1, up 2. Good. So if this is the case, each of these points going to move left 1, up 2. So left 1, up 2. Approximately right there. I think I went a little bit too high. Okay, what about my asymptote? The up 2 isn't really going to show up. But left 1, yeah, that's going to happen. So my sketch, we could start it and we could end up here. But there is a catch. Every time we have a natural logarithm, we want a third point. Okay? And the reason is that because this second point isn't precise, isn't exact. Again, if you think about it, the first point, we can label that first point, no problem. That's at 0, 2. The second point, this is going to be a little bit trickier to label, isn't it? Remember that we were at E1. I went left 1, so would we agree that's E minus 1, comma, 1 up 2 was going to be located at 3? Everybody see how we got there? Okay, sorry, give me one more second. So how am I going to find this third point out here somewhere? T-chart, and it's up to you. I'm going to pick 8 because that's the furthest we go over on the graph. Okay, but other than that, guys, everything else is going to stay the same. I'm going to pause this video here. I'll finish it All right, so back to this problem. If we're going to take a look at it, as we got these 2 points, again, when we shifted left 1, up 2, our points are going to be, I'm the wrong part. We're going to be hitting here and here. But like I said, we need to come up with a third point. So if we have our choice, I'm going to go with 8, simply because that's the furthest to the right while still being on the graph. Again, nothing against choosing a value of 10 or 75 or 6 or anything else. I'm just going with the value that's going to be giving us that point that's furthest to the right of the graph. So when we say that we're going to be plugging in, let's see what we're talking about. We're talking right here. So if we're looking at the natural log of, now not x, but 8 plus 1 plus 2, putting up inside of our parentheses, definitely have to follow the order of operations. We're going to say that y is equal to the natural log of 9 plus 2. And here's the spots where we cannot afford to make a mistake. Natural log of 9 has to be taken before we add 2, meaning we don't want to go with the natural log of 11. That follows order of operations. We're going to clean this up and get approximately 4.2. So when we plug an 8 in for x, we get 4.2 back out for y, which is going to lead to that third point that we were seeking over 8 up 1, 2, 3, 4.2. Again, not exact, it's approximate. But now we know approximately where that sketch is going to go through. I've got to erase some of this stuff so we can have room to provide our answers. So if we were to identify that vertical asymptote, remember we had different ways that we could get there logically using the graph, or at the very beginning setting that set of parentheses equal to 0. We're going to land at x equals -1. Our domain in that case is going to be not including -1 to infinity, and our range is going to go from negative to infinity to infinity. So our goals for this particular section, I'm feeling pretty good about where we're at. Again, graphing the log functions, it's a pattern. Once we recognize that pattern, we just have to practice, and that's the mode that we're in right now. Again, that yellow worksheet in our book work should give us some opportunities to practice tonight. Those will be due tomorrow. Exchanging back and forth from log to exponential form, something that we covered yesterday that we touched on a little bit more today. And then 3 and 4, the one-to-one property, as well as simplifying with our other log and natural log properties. That's going to be a big deal. So again, 218, you've got the mandatory as well as the yellow worksheet that's going to be due tomorrow, if I can remember what I was trying to say. Other than that, have a great night.